What's up, everyone? It's me, Miss Wesley, and well, it's pre-calc time. Yes, you read the top of this packet correctly. Today is a huge day as we get into Calculus Chapter 1. I'm curious to hear what you think of when you hear the word calculus, what comes to mind. And there are three major areas of it. You start with this thing called limits that we'll begin with today. You move into rates of change called derivatives, and then it's the antiderivative. Then you talk integrals later on in the process. So I'm going to pull examples. We're really going to start on page 2 of this packet, but I'm on page 1 for a second just so I can gaze at these beautiful emojis that I have at the top. They were my best. I just got finished watching Outer Banks, so those are my best Pogue Life emojis to put at the top there. And we'll get into some of these examples in a second. A little joke for you to start. What do you call the guy who has no nose and no body? Nobody knows. Now, let's think. If not a lot comes to mind when you hear the word calculus, that makes sense. We haven't gotten to it yet. But if I think back to my old days of algebra, geometry, and pre-calc, a common question to be asked was, if I have a function that's linear, any teacher ever ask you to find the slope of the line f of x? That's a common question, a rise over a run. It would be weird to ask you the slope at this point and to follow it up with the slope at this point or that point, because that's something about a linear function. The slope, or the rate of change, is constant throughout the line. Well, not all functions are linear, are they? We've dealt with quadratics and cubics and exponential and logarithmic curves, trig functions as well. So calculus is the mathematics of change. One of the main areas you're going to get to in calculus, one of the main kind of problems that it's centered around, is dubbed the tangent line problem. And here's a little explanation of it. Maybe you have some real life situation where you can't model it with a linear function. You've got this door that you push open really quickly and then it slowly comes to a close. And you're going to graph the amount of degrees that door is open versus the amount of time it takes to get to those degrees. And you have this little model here with this equation. If you type this into the calculator, I'm going to give you a rough sketch. The door starts closed, it opens wide, and then it slowly comes to a shut. You get a picture that looks like that. And I might just pick an arbitrary point on this function, on this curve, let's say this point over here, and I might say, what would the slope be? Or what would the rate of change be at that point? I don't know if you've been asked about the slope of a curve before. There are good ways you can estimate it, and that's where limits are going to come into play. But this tangent line problem is, okay, well, calculus has an answer. You're going to calculate a derivative. So if I can get that line a little bit closer, the tangent line would just brush the curve at that one point, just touch it once. If we could get the slope of that blue line, that is what's called the derivative. That's going to be the rate of change at that instant, right? It should be a negative value because we're on a downward trend of that curve. Now, what I want to do is actually skip over this exploration for a second, go straight to page 2, and give you guys some background about how you find a limit on a graph or a table. I would say now's a good time to have your calculator handy because we are going to use the table feature a good bit in these examples. So it says definition of limit. If f of x, and this is easier to see when you visualize the graph, if f of x becomes arbitrarily close to a value, to a unique number L as x approaches c from either side. So here is some arbitrary x value c, and I'm going to call the point where it touches the curve, I'm going to say that has the y value of L, like that. And I'm going to write this out in words. What we say is the limit of the function f of x, so of f of x, as x approaches c. I'm even going to put in parentheses here, from both sides. That's going to be understood. Is going to be L. As x approaches the c value from both sides, the y value attained by the function is going to be this L that's on the other axis. Seems kind of self-explanatory, and we have some notation for this, some new calculus notation for writing a limit. We're going to write limit LIM. Underneath of that abbreviation for limit, we're going to put what x is approaching. So limit as x, I'll say arrow c. As x approaches c from both sides of f of x. So here's another case, kind of like if you were to just write sine and put nothing after it, it has no mathematical meaning. Or if you were to put a square root and nothing inside of it, doesn't have much meaning. Same thing here. The limit notation needs a function after it. So of the function f of x is going to equal the y value L. All right, now let's see if we can work with some simple functions like a 3x minus 2 seems kind of tame, and work up to some more complicated ones down the page to calculate our first limits ever together. This is exciting. Can we make a table, but we're not going to set this table up of values for this function like you would typically set up a table to be able to graph it. I mean, graphing it is no big deal. We'll save that for the end, but it is just a line. This one shouldn't be too bad to do by hand. I want to put the x value that we care about, limit as x approaches 2, I want to put that directly in the center of the table. And instead of just approaching it from both sides with the same increment of whole values or fractions of values, I want to get increasingly closer to 2 from the left and increasingly closer to 2 from the right. Here's what I mean. I want to go 1/10 below 2, so 1.9, all the way up to 1/10 above 2 symmetrically, all the way up to 2.1. I want to get increasingly closer to 2. So this was only a tenth away. The next value I'm going to arbitrarily pick is going to be 1/100th away, 1.99. How about 1.999? These are frequently how the tables are set up to calculate these limits, but these are not the same increment going up to 2. They're getting increasingly closer to 2. Could you fill in the symmetric y values? Go 1/100th above it, 2.01. And only 1/1000th above it, 2.001. And I'm going to let the calculator do the work to get the values here because I want to watch the y's also approach a value. So for this to work, I'm going to go to y equals, clear out any equations or stat plots that I would have had on before, get myself back into function mode rather than polar, and I'm going to type in the original function, 3x minus 2. Okay? And instead of going straight to a graph, let's go to a table. So I'm going to check my table settings. Second in window. I'll start at maybe 2. Actually, it doesn't really matter for what I'm about to do. Delta table can be 1. Here's what really matters. I want you to keep your independent variable on ask. This is, if you remember, the setting that lets us type in any x value and it'll spit out the corresponding y. And dependent should be on auto, so it gives you that. I'll hit second and graph for table. I see a blank screen. If you've got numbers filled in, that just means you typed in numbers previously and you can overwrite them in this step. So I'm going to type it in exactly in the order I see it. 1.9, I'll do 1.99, and then 1.999. And these values are what you can copy straight into your table. Look at what they seem to be approaching. 3.7. 3.97, it's creeping up to a curious whole number. 3.997. It looks like it wants to be a 4 here. I bet this is exactly a 4. Let me go back to the calculator and see. When I type in 2 exactly, I've taken away the suspense. These numbers are approaching 4 from below. When you go above it, is it very surprising? Just 1/1000th above it should be right above 4. 1/100th above it. And then just like the table set up, I put a 2.1 at the end. You see the same thing happening on the other side. I got a 4.3 way above 4, 4.03, and 4.003. So these values, you can see the y's rising to 4 and falling from above 4, right, to 4 on the other side. The limit, you're going to say, is the number 4. If the x value is here, the y value goes there. Now, you might be sitting here thinking, Miss Wesley, this was really obvious. I needed a calculator. I didn't need a calculator nor a table to get this value, because if I asked you what's f of 2, if I say what is f of 2, that is also 4. If I plugged a 2 into this expression, I would get 6 minus 2. Let's see this visually on a graph. We have to work with the easy ones so we can get to the tougher ones in a second. On a graph, this is a line that shifted down 2 units, and the rise over run is going to be up 3 over 1. Now, not my best work, but you get the picture. Here is the point in question that we really care about. As x approaches 2 from both sides, the y value is approaching 4. And in limit notation, we would say, well, f of 2 is the same exact thing as the limit as x approaches 2 of f of x. And in both cases, you get 4. So the function value is the same as the limit. If you'll excuse me, one last little illustration before we move on. Sometimes it's tougher to get a limit than it was in this case. I pictured 2 guys walking along a function. So here's my little stick figures here. They're trying to walk towards each other and they're trying to get to each other. As they approach the x value 2, the limit is going to be the y value where they meet up. If this guy's walking this way, that guy's walking down to meet him, it's a happy story because they'll meet right at that point. Okay. Now let's kick it up a notch. In 2 and 3, we have in both of these a big domain restriction that's going to prevent us from getting an f of that number. There is no f of 0 in this case. If I tried plugging in 0 to this expression, I'd have 0 over 1 minus 1. I'm going to get an undefined value. But what we're going to learn in 2 and 3 is the existence of a function value at 0 has no bearing on the existence of a limit. There is still going to be a limit answer for this question. So let's illustrate it. Can we get increasingly closer to 0 from both sides symmetric? I want to use kind of the same proportions here. I want to go from negative a tenth below 0 to a tenth above, or negative 0.1 to positive 0.1 is what I meant to say there. Then I'll get increasingly closer, negative 0.01, negative 0.001. So just creeping up to 0 from the left side. I want to creep down to 0 from the right side, like that. And I'll use the calculator to just get some expressions here. I got to do this quick, and I'll go to y equals, clear out the last equation, and type this one in carefully. Let's put parentheses around the denominator. X over square root of x plus 1 minus 1. All right. So then I'm going to go back to my table, second and graph for table, and I'm just going to overwrite the numbers that I put in there last time. So from negative 0.1, negative 0.01, and negative 0.001. Okay, and I'll see what those numbers are telling me in a second. 0 is going to be kind of boring because we know you get an error message there. 0.001, 0.01, and 1.1. Take a look at those outputs that the calculator just gave us. Can you make an educated guess as to what you think, what numbers being approached from both sides? I mean, there is no f of 0 here, but it looks like the numbers are, and I copied them into my table already. They're creeping up to 2 from the left side. They're creeping down to 2 from the right side. So all educated guessing makes me think that the limit is probably 2, and it is 2. And there are algebraic reasons why it's 2 as well. There's actually tricks. In the future, we're going to rationalize this denominator to be able to graph this and see if we can get something to cancel out to do it easier. For now, I'll just show you the picture. If you were to graph it, you get this square root shape that's shifted up and over. And it's going to have a hole in it. There is no f of 0 that we can find, but there is a limit, right? We're going to say f of 0 is undefined. We saw that in the table. The limit, however, does exist. Limit as x approaches 0 of the function f of x does equal 2. Picture the dudes that I said were walking along the function trying to get to one another. This guy's walking from the left. That guy's walking down from the right, and even though there's a hole that they're walking toward, right, they're going to meet at the same spot. Sure, it's an open dot, but like I said before, the existence of a function value there has no bearing on the existence of a limit. The limit is going to be 2. So there could be a limit even when a hole is concerned because the meeting spot is the same. The third one's very similar. It's a good follow-up. If you type this into your calculator, I'm going to let you pause the video now and get the numbers, and I will write in what my calculator gave me. I want 1 to be right in the middle of the table, and I want it to be approached from the 2 sides. So I'm going to go a whole tenth below 1 to a whole tenth above 1, 1.1. On the other side, I'll go 0.99, 0.999, and then above it 1.001 and 1.01. And the calculator didn't give me any value for f of 1. I noticed that makes the denominator 0, but I wonder if there's still a limit. Well, my calculator gave me 1.81, 1.9801, so creeping up, 9801, and then 1.998. These values seem like they're creeping up to 2 again. I'm wondering if the limit is 2. Well, from the left, it looks like it. From the right, it does as well. 2.05 when rounded, 2.005 the calculator gave me, and 2.0005. And that's enough confirmation for me while I'm just guessing. I'm going to estimate it looks like these values are limiting off to the number 2. And this we would have known by doing some algebra. If you factor up the top and cancel it with the denominator, you'll see the calculator gives you a parabola here with an open dot at what point would have been 1, 2. The 2 people walking along the function would meet at that hole, and the limit equals 2 despite the fact that there's no function value there. All right, we're going to tune back in and discuss existence or non-existence of limits. See you soon.